go ahead and get started. Before our seminar today, Alex would like to say a few things about the department's YouTube channel for disseminating the videos that the graduate students have been processing. So we'll let him get started, and then we'll proceed with today's talk.
All right, thanks, Dr. Leffer. Yeah, I just want to give a quick reminder to people. You probably see me here recording all the seminars here this semester and last semester, and I've had a few questions on how to access them and where you can find them. The GSA has a YouTube account that these have been posted to so that everybody can access these videos both for reviewing your own presentations as well as if you miss a presentation that may have been interesting to you. In order to find these, you can simply just go to YouTube and it's NRM GSA, or you can type in NRM seminar and it'll come up. This right here is our overall page. Otherwise, you can find our different seminar playlists and stuff. So I have them split out by spring and fall seminar. You open those up and see, here we've got Travis's roundabout video. Otherwise, if anybody has any questions, you can contact me directly or Dr. Leffler, and he'll send you to me. As well as I am working my way out, the GSA will be looking for volunteers to take this over if this is of interest to people and want to keep the videos going in the future. So if you're interested in that, contact me. With that, I will hand it over to Dr. Leffler.
Okay. We lost the... Okay, then I am pleased to introduce Aaron Suehring, who will be giving us his completion seminar on the assessment of watershed condition and vulnerability to forecasted land use land cover change in the Northwestern Great Plains of western South Dakota.
All right, thank you, Dr. Leffler. So I'd like to acknowledge funding and support for this project, which have been provided by the South Dakota DENR, South Dakota State University, the Agricultural Experiment Station, and the Oak Lake Field Station. And I'd also like to thank my advisor, Dr. Knowles Trollstrup, and my committee members, Dr. Mike Wimberly, Dr. Sandy Smart, and Dr. Carrie Steinlich. So in the past 50 years, the global population has more than doubled. And by mid-century, it's projected to increase to over 9 billion people. This increased population is undoubtedly going to cause an agricultural intensification. Nationwide, 46% of our nation's streams are in poor biological condition. The leading causes excessive nitrogen and phosphorus in the waterways. These two nutrients are commonly cited as sources of water quality inherent from agricultural practices. And in the state of South Dakota, the story is even worse. Just over 78% of assessed streams and rivers were listed as impaired, due predominantly to livestock and crop production. So we know the landscape influences the surface water quality in the stream. And with the projected increase in agricultural intensity, extensive landscape level water quality monitoring is going to be especially important in agriculturally dominated regions in order to better focus limited management resources. So the objectives of this project were to generate watershed condition scores for wadeable perennial stream watersheds in the NWGP of South Dakota, determine if the response of watershed condition to landscape drivers varies by level for each region, determine watershed vulnerability to land use and land cover change under multiple scenarios of development, and lastly, to define priority watersheds for protection and restoration. So the NWGP comprises most of western South Dakota, excluding the Black Hills and some parts in the south, and it's mostly grassland, dominantly grassland, And for our study, there were 1,025 watersheds that met our minimum size requirement to be considered wadeable perennial stream watersheds. And you can see they're shaded by the 10 level 4 ecoregions within the larger NWGP level 3. So to generate the watershed condition scores, we generated a whole suite of watershed characteristic metrics with the Analytical Tools Interface for Landscape Assessment, or the ATILA program. ATILA is a GIS art toolbox written by the EPA for the purpose of landscape assessment, and it generates metrics grouped broadly under landscape characteristics, riparian characteristics, and human stressors. So in total, we generated 226 different metrics from these spatial layers. And I do want to point out that for our land cover layer, we used the 2011 National Land Cover Database, or NLCD, because I will be coming back to that later in the presentation. So to get the number of metrics down to a more manageable number, we had to put them through a screening process. So we evaluated the relevance to surface water quality, took out any redundant metrics. Metrics with a large percentage of unvarying values were also removed. The remaining metrics we put into a principal components analysis, from which we retained the first 3 metrics from each of the first 4 principal components with the highest vector loading, accounting for just over 70% of cumulative variance among study area watersheds. These metrics we normalized from 0 to 1 just for comparison purposes, and then we weighted each metric according to the percent of variance accounted for by the principal component from which it was selected. So basically, metrics from the principal component 1 were weighted more heavily than those selected from principal component 4. So these we summed to create a raw watershed condition score, and then rescaled that from 0 to 100 for communication purposes. So here you can see the final list of metrics that went into watershed condition scoring and the principal component that they were selected from, as well as the percent of variance accounted for by each principal component. And then the spatial representation of watershed condition, where the dark red indicate watersheds in the worst condition and dark green indicates watersheds in the best condition. So overall, the distribution was skewed towards watersheds in better condition. And to me, this makes sense, right? Because most of western South Dakota is grassland. And we know grassland has the ability to prevent erosion, filter sediment and runoff, and absorb harmful chemicals and nutrients that would otherwise end up in waterways. So to me, this makes sense that the majority of watersheds would be in better condition. And broken down by the 10 level 4 ecoregions, which I showed earlier, you can see watersheds in the dense clay prairie were in some of the best condition, There's a lot of grassland, a lot of shrubland, not a lot of human disturbance in this region, whereas watersheds in the agriculturally dominated Missouri Plateau were in the worst condition. So next we wanted to determine if the response of watershed condition to landscape drivers varied by level 4 ecoregion. So the idea of this objective, we wanted to compare the response, or the slope coefficient, of watershed condition on each landscape driver that went into watershed condition scoring. And we wanted to compare that for each level 4 ecoregion relative to the larger NWGP. The reason being, if we are seeing a lot of differences by level 4 ecoregion, this would support the use of a level 4 ecoregion framework for water quality assessment and monitoring. And second, if a level 4 ecoregion was, let's say, more responsive to human use than the larger NWGP, so it has a more steep slope, it decreases at a faster rate, this would suggest that protection measures should be given priority in this level 4 ecoregion, where you're going to see a faster decline in watershed condition. So to do this, we regressed watershed condition on each of the landscape drivers and compared the slopes of the level 4 ecoregions to the NWGP with a comparison of regression lines function in statistics 10. And these are just 3 examples of what we were getting at. So you can see the level 4 ecoregions are in orange, and in black is the NWGP as a whole. And so these 3 were all significantly different. So you can see the top 2, they decrease at a faster rate, so they have steeper slopes. Whereas the one on the bottom has a more gradual slope, it increases at a slower rate. So overall, we found differences among 40% of the comparisons. Watershed condition was more responsive to anthropogenic variables in the Missouri Plateau, subhuman plains, Kippaha, and semi-arid plains. And also it was less responsive, so it had a more gradual slope to the natural land cover variables in the Kippaha and semi-arid plains. So that's especially important for these 2 ecoregions to protect them, because these 2, watershed condition decreases at a faster rate, the anthropogenic variables, but it also increases at a slower rate with these natural land cover variables. So once it's in bad condition, it's going to be harder to bring the condition of watersheds in these areas back up. So our third objective, we wanted to determine watershed vulnerability to land use and land cover change under multiple scenarios of future development. To do this, we obtained forecasted land cover data from the forecasting scenarios model, or the 4C model. The 4C model forecasts land cover change on an annual basis through the end of the century under 4 scenarios governed by assumptions dealing with population growth, technological advancements, sustainable resource use policy. And they're oriented along 2 axes. So the economic and environmental, that's fairly self-explanatory. And then the global and regional extent, global refers to increased cultural and social interaction. So there's more global solutions to environmental sustainability. Whereas the regional extent, you don't have that cultural and social interaction. So the technological advancements, the economic development is more fragmented. So for the purpose of this study, vulnerability we defined as the potential of a watershed to undergo land use, land cover changes that result in detrimental surface water quality changes. So to do this, we obtained land cover maps for 2011 and 2100 for all 4 scenarios from the 4C data set, the forecasting scenarios model. We generated the landscape metrics that went into the watershed condition scoring using these 2 land cover maps. And we found a percent change between the 2 years. We took that percent change and applied it to the original National Land Cover Data Set, or NLCD metric value, that was used to calculate a watershed condition scores. So then we're able to get a National Land Cover Data Set metric value for 2100, so to speak. We recalculated watershed condition score using that metric value, or that set of metric values, and then found the difference between the 2011 and 2100 watershed condition score, from which we were able to get a vulnerability gradient. So it was consistent across all 4 scenarios, but it's especially noticeable in the 2A scenarios, economically driven. So watersheds in the Meraux Prairie were most vulnerable to land conversion. But what I think is even more interesting than the spatial representation is the variation in scores between scenarios. So you'll see in both A scenarios, there's a larger percentage of scores above 75, so really vulnerable watersheds. And this is because in both A scenarios, the overall magnitude and the intensity of land conversion was much greater. So you're seeing some watersheds that are suitable for this land cover change are undergoing large amounts in high intensities, while others are not. So you're getting a big spread. Whereas with the 2B scenarios, the overall magnitude and the intensity is much lower. So you're getting a lower intensity of land conversion dispersed throughout the region. It really brings in that variability. Our last objective, we wanted to define priority watersheds for protection and restoration. To do this, we put the watershed condition score on the x-axis and vulnerability score on the y, and the lower 50th percentiles of both. So the watersheds in poor condition, not vulnerable to change, make them restoration watersheds. And then vice versa, the upper 50th percentiles we wanted to protect. We further broke it down by the upper 25th percentiles, so your really good condition watersheds that are really vulnerable to land conversion, make it a priority to protect those. And then other end of the spectrum, the really poor condition watersheds, not vulnerable to change, make them restoration priority. So here you can see the data values for all 4 scenarios. And again, you can notice the tighter variation in the 2B scenarios. And looking at the maps, fairly consistently among scenarios, you have watersheds in the Missouri Plateau and the northern part of the semi-arid plains classified as restoration priorities. So if you remember back, these were in some of the worst condition today. So they're already dominated by agriculture. There's little room for further agricultural expansion. Therefore, they have low vulnerability scores. And it's most noticeable in the 2A scenarios, grouping of watersheds as protection priorities in the Moreau Prairie. And again, these were areas, watersheds that were relatively in good shape today, but they're expected to undergo a lot of land conversion. So you want to make those a priority to protect them. So similar to other studies that have used the Attila program to examine landscape characteristics, we incorporated Attila and developed a methodology to assess watershed condition across a broad landscape. And our results support that there's many differences in watershed condition in western South Dakota. And it's not just one big homogeneous grassland. What we did find that watersheds in the Moreau Prairie were most susceptible to forecasted land conversion. And although other agencies have looked at watershed vulnerability, not to my knowledge, none have used such a dramatically detailed forecasted land cover map. And this methodology allowed us to prioritize watersheds for protection and restoration. So like I mentioned, this supports the appropriateness of a level 4 ecoregion framework for water quality monitoring. And it can be used at many different spatial scales, and managers have the ability to incorporate many different data sets or data projections to suit the needs of their specific project goals. Although the results aren't meant to identify fine-scale sources of impairment, these results can be used to target at-risk watersheds to get out there and see what's really driving this impairment. And the tools here may provide an effective means for long-term planning and targeting management efforts to better conserve the state's aquatic resources. With that, I'll take any questions.
So, obviously this is all hypothetical because it's just playing around with GIS stuff.
Pretty pictures.
What data do you actually have that could be used to ground truth to show that the water is actually as good or bad as normal?
Yeah, so I guess after we made these, we went back and looked at the 2016 South Dakota Integrated Report for Water Quality Monitoring. And each of those ecoregions that were in the worst condition, they all ran through basins that had major rivers listed as impaired. So we kind of retroactively went back and it helped validate our results.
You probably said this, but what does restoration mean? Like, to what level is it restored? Is it restored to what it was naturally? Did you say that and I just missed it?
I didn't mention it, I guess. It just to bring it out of impairment so it meets its beneficial uses. So you can go out and say, what do we need to do in this stream to help restore the beneficial uses? Do we need to keep the cattle out? Do we need to work on the riparian area?
But is there any kind of data-driven thing on that, or is it more? What I just heard was more subjective, but it could be wrong.
Yeah, I guess, and that's something you could determine once you get out to each watershed and see. What's causing the impairment, and then whatever that would take to help the water quality meet its beneficial uses again.
Could you tell us a little bit more about some of your statistical analyses, specifically how you treated the watershed condition score, which is a bounded variable, can't be lower than 0, can't be greater than 100, so it's just like a percentage. And it's really obvious that you're getting a lot of non-normality influences in, especially like the regression analyses you did, where everything kind of converges on 100% or on 100.
Yeah, as far as the slope comparison, so we did compare the variance, so that was one of the criteria in order to compare the slopes. And so total, I think we had, with that slope comparison objective, we had 42 comparisons we were able to make, of which 17 were different. So because there weren't equal variances, we tried different transformations for the data. So we take the natural log of the predictor and the response, as well as we tried rank transforming both, and we'd retest, and just to see if it helped meet the assumptions.
What transformation did you wind up with for the watershed score?
For the watershed score, we didn't do any transformations for that. That was
Oh, really?
I mean, I guess we selected the metrics, and then whatever their values were, they were normalized, summed, and then rescaled.
Yeah, Aaron, could you, going back to the question in the back of the room, discuss linkage of the results of a watershed showing a poor watershed condition overall, and the actual field work that's going on in the other part of the project, which is actually collecting field data. It actually gets to part of Sandy's question too, about how do we know if watersheds are in good condition or not.
Yeah.
Because that whole field component of the project really isn't a part of this presentation, but it's linked. And then also the TMDL process that would lead to the identification of sources of impairment for beneficial uses in a targeted watershed.
Sure. Yeah, that's a good point that I didn't mention. So there's a concurrent part to this project that's going on right now, which will be presented in a couple weeks actually, where they're developing fish and invertebrate IBI, so an index of biotic integrity, in these streams. So basically a measure of the stream's health, so to speak, based on the biota that are present. And they're also looking at different habitat measures, different water quality characteristics in the stream. And so that'll later be tied into these watershed condition scores. So we'll try to get hopefully a fairly tight correlation between what they're seeing in the stream and what's being presented here.
Aaron, could you map the 303D designations where they're impaired, and then layer that on top of your map? Because you can see, if you go into those integrated reports, they'll color code the streams or lakes and why they're impaired. And I'm wondering if you could then take that layer and layer it on top of yours. It would probably line up with your red areas would probably be impaired. And I was wondering if there's a possible way to even develop a correlation statistic between, what's showing up as impaired and what's not to your designations of your scale. That'd be just another way to validate, to show that. But I wonder if you could actually calculate a statistic.
I mean, as far as obtaining a layer, I'm sure that would be feasible.
Because DNR probably has that layer.
Yeah, they do. Yeah, so that would be.
And you could calculate, I don't know how, somehow if you could get the GIS or somewhere score the impairment to have some type of score, and then use that to correlate to your watershed score, and then you can generate a correlation stat.
Yeah, that would be something interesting to look at.
So we have a question from West River. Jamie asks, are there specific recommendations you would make to farmers and ranchers interested in protecting and restoring watersheds of interest?
I guess I would say riparian area is always a big issue with I guess keeping cattle out of the stream, so you get that good healthy riparian area to help prevent erosion for one thing, help bank undercutting, keeps a lot of the sediment or the nutrients. It acts as one more way to keep the sediment and nutrients out of the stream.
Any other questions? All right, one more round of applause. All right, thank you everybody. See you next week.